All right, now we want to do the full fluid calculation. Let's say that we didn't get that water table, and we're not sure where the water table is. And actually, it turns out if you do the full calculation, the water table does not show up where on that surface, which is what a sort of simplified analysis would. The pore pressure distribution, you get R a little different, right? So let's say what we know then is we know that on the way up slope, this is the pore pressure distribution, and way down slope, this is the pore pressure distribution. So we want to calculate what that curve looks like rather than assign it, okay? Now we need to know some new properties. We need to know the permeability or the mobility, or in the new version of the code, we actually call this mobility coefficient, right? Clear on what permeability, which permeability you're using and what your source is. You have a lot of problems with people coming from like petroleum and having a permeability that means something different. Make sure you're using the right one, okay? Porosity, how much space is there for fluid to flow in? The fluid tension limit, this is where it breaks and becomes unsaturated. So you generally, if you want to allow unsaturation, you want to set that to 0. The zone water density, now that we're in config fluid, before water density was before you config fluid, water density was a global. You set water density, it was a single value, everybody used it. Now that we're in config fluid, technically every zone can have a different water density. Why you want to do that is not obvious. It does come up in certain, especially thermocoupled problems where density is changing because of heat effects and stuff like that. But for the most part, just remember that you can initialize fluid density here. If you don't and you forget, it will by default use the global value, but you should really initialize it here. Also be aware, you'll note that some things are set in grid points and some things are set in zones. For instance, fluid tension and fluid modules are set in grid points. Fluid density is set in zones. The new version is going to fix all that. Everything's a zone property. But for now, you've got to keep track of which is where, because some things are properties, some things are grid point values, and some things are zone values. And that has to do with whether it's considered part of the fluid constitutive relation, or where the math is happening. So, for instance, density is applied to the zone, so it's stored in the zone, whereas fluid tension and fluid modulus is part of the constitutive relation for a grid point, so it's stored in the grid point. For now, it's probably best if you just remember and look at these examples to remember what's where, okay? And then know that when the update comes up, life will get a lot simpler. Note that you're setting the water bulk modulus here, and this is a super important property because this controls, this is basically how stiff water is. Now, as we all know, water is pretty stiff. And if you're doing mining, this might not be a big deal because the rock you're doing with is also pretty stiff. If you're doing soils, there can be a big difference between the actual real fluid modulus and the soil modulus, and that can cause numeric problems and a lot of trouble. And so you end up playing a lot of games, adjusting your fluid modulus to give you an accurate response without taking forever. We're going to talk more about that later, hopefully, okay? Note that it is possible, and you'll see it done, to set the fluid modulus to 0. This is done essentially as a trick to turn off two-way coupling while you're doing mechanical cycles. If, for instance, you've got your pore pressure field and now you're going to cycle mechanically and you don't want it to change the pore pressure field because of volumetric changes, you can set the fluid modulus to 0, and that's essentially turning that coupling off for a while, and then you turn it back on. You set it to a non-zero value later. Bulk modulus of water, 4.18 e to the 7 pounds per square foot, or 2 GPa. Okay, that's a high number, especially if you're doing soils. If you're doing steady state flow, the fluid modulus is irrelevant. Steady state is steady state. For the steady state solver, it's not even an input property. It doesn't matter. It's only important for transients. So if all you want to do is get to steady state as fast as possible, you want to set it to sort of an optimal value because FLAC2D in your version only does transient calculations. How to speed it up? Generally, you lower that to an optimal number, and this is the number you want. It's roughly 0.3 times a characteristic length, basically the length of your zones in the region you're most worried about, and then times water density times gravity. This is sort of a rule of thumb for setting a non-realistic bulk modulus of water to converge to the steady state solution as fast as possible. If you're doing a transient analysis and timescale is important, but you still don't want to use the full fluid modulus because then things take forever, your time step are tiny. You can still play games. And what's important here is the ratio of the mechanical stiffness to the fluid stiffness so that you're not completely out of range of reality. So then we have a different rule of thumb. We adjust things according to this relation. And again, I'll cover it more later. This looks crazy complicated, but you can see you're basically using the porosity and you're playing games with the relation of the stiffness between the material stiffness. This is essentially the confined modulus of the material and the fluid stiffness so that they have the right ratio. By the way. This is sort of considered a limit. Also, you need to account for the deformation of the solid. So remember, saturation will be calculated automatically, assuming it can break the fluid tension. Note that there's no need to specify wet density. You specify dry density everywhere, and it wets it. It calculates the additional density due to water for you. Now, as soon as you config fluid, okay? You are going to need pore, or you are going to need fluid boundary conditions, pore pressure boundary conditions, whether those are fixed pore pressures or discharge rates or whatever, okay? You are going to need to set some, in order to have a model, you're going to have to set some sort of boundary conditions, just like mechanically. What boundary conditions are there? Well, if you don't specify a boundary condition, it's impermeable by default. So if you don't specify anything, it's just an impermeable boundary. You can fix the pore pressure to 0. That's a free surface that water can leak out of for whatever reason. And you use that with the zone face apply pore pressure 0 command. You can set a pore pressure 0 value. Typically, this is whatever the hydrostatic gradient is in your far field. Okay. So for instance, you zone face apply. This is the bottom, and then it's smaller as you go up because this is essentially gravity times fluid density. All right. That's assuming that the bottom is 0, but in any case. Or you can do a discharge. So you can see there's a constant inflow or a constant outflow at a certain point. Often this is used in like a well, not necessarily on the boundaries of the model, but you can say, I've got a well here that I'm pumping water out of, so you can give it a constant discharge rate to simulate that, okay? So what are the steps? First, you turn, if you want to do a one-way couple analysis, you've already configured fluid. So now what we're going to do is we're going to turn fluid on and mechanical off. What that means is FLAC2D has got an awareness of what processes is what it's called are active, the mechanical process or the fluid process. By default, if you config fluid, the fluid process is on and the mechanical process is on. And if you take a step, you're going to do a fully coupled analysis. It's going to do the mechanical and the fluid at the same time. Very rarely is that what you want. So here, what we're going to do is we're just going to do a one-way analysis. We're going to solve the fluid field by itself. So we're going to say model fluid active on, model mechanical active off. So we could just say model mechanical active off, but that's okay. We're being clear. We're initializing the fluid modulus for steady state calculations. So we do this thing. And then we solve to a fluid time of t, where t is in seconds based on the system of units we're using right now. And t is big enough to say we're going to be at fluid equilibrium, at steady state flow. And then we turn fluid active off and mechanical active on again. Now we've got our pore pressure field. And then we set our fluid modulus to 0. This is so we turn off two-way coupling. Now when the zones compress, they're not going to generate pore pressure because the fluid modulus is 0. And then we solve the mechanical part. Okay? And that's what this data file is doing. If you look at slope GW, oh, where'd my mouse go? Slope GW. I hope that's, whoop, there, slope GW. We're going to config fluid. We're going to reset the displacement and state field again, just like we did before. So we see, if just right now, we need to assign the isotropic permeability model to the fluid. This is a step that's not necessary in the new version of the code because that's the only constitutive model anybody ever uses, basically. It's always a linear model. It's just whether the mobility coefficient is a tensor or a scalar. So we just got rid of the whole idea. Set your permeability, you set your porosity, you set your fluid density. So these two things are considered properties. This is a zone parameter, and then the fluid modulus and fluid tension are grid point parameters. Again, I understand that's confusing, and it will be simpler later, but for now, just remember. Okay. Now, because of a bug in the current version that will be fixed before release, hopefully, we have to actually remember this stuff that we went to equilibrium. When you do the zone relax excavate command, that gets nulled out automatically. There's some bug that's refusing to let us apply a boundary condition to the surface, and we actually delete those zones, even though they're nulled. That shouldn't be true, and it will be fixed before release, I hope. So for now, for the purpose of this test, we have to explicitly delete them, because then we can apply 0 pore pressures to this surface, because it's important that that surface have 0 pore pressure. How am I doing for times? Right, better than last time, but still not right. We apply a 0 pore pressure to that surface. Now we also apply pore pressures to the left and right. And here we're doing hydrostatic gradients, assuming it's 14 foot high on the right and 5 foot high on the left. So it's about yay high on the right. On the left, it's all the way up to the bottom. And if you look at that data file or the commands, you can see, oh, here, I can make that bigger if anybody's having trouble seeing. We do that with zone face apply. We give a pore pressure, and we can use inline fish to make these calculations simpler rather than do it in a calculator and type it in. We can let FLAC2D do the calculation for us. Gravity times the depth. And then with the gradient of negative gravity, on the right and on the left. So we've got two different, a higher one on the right and a lower one on the left. We take a history of pore pressure at some representative point in the model because we want to see how that's changing. We turn mechanical off because we only want to do a fluid calculation. And then we solve, and instead of doing a time, I'm doing a ratio flow. This is a solve parameter that's only available when you're doing flow modeling. And what this is, it's a convergence metric that's based on inflow versus outflow over the entire model. So it's basically saying the inflow over outflow, right? If everything's in full equilibrium, the inflow and outflow match perfectly. This is saying that it's allowed to be 1 minus 3 out of ratio, and we'll call that close enough, okay? It's an imperfect metric, but so are all of them. Okay? Now that we've got our, and then we call this slope GW1. This is our fluid equilibrium. Then we turn mechanical on and fluid off again. Remember, we don't want two-way coupling in this example. So we set our fluid modulus to 0 so we don't generate pore pressures due to volumetric compression. And then we solve mechanically. So now we get the same answer before, but instead of using a water table to calculate the phreatic surface or in the pore pressure field, we use the built-in flow logic to do it in the most efficient way we can. So if you Take another plot here. Here we go. Okay. Let's run that. Just look at GW, and we want to look at pore pressures. So we can see it now. It's doing that transient analysis. It's calculating that surface, and then when it's done, it's going to start doing the mechanical calculation, and that's going to stay fixed because we've turned fluid modulus 0, so it's one way. Now we got a pore pressure field that was calculated given the boundary conditions as opposed to one that was assigned. And you'll note that if you look at the two different states, here versus here, they're not the same. Okay. That will have some effect on the failure. Go here to displacement, you can see it's actually significantly different. The water table was higher in the first one than it was in the second. So it caused more failure. Let's quickly go to the next. Okay, now there's a fully coupled analysis here. You can see zone coupled. Now this one, we figured the timescales are the same. So we do the same thing we did before. But oh no, sorry, we'll do a fully coupled analysis. We're gonna do a fully coupled analysis starting from this state. I'm misremembering. We drop the water table. We say for some reason the water table is dropping by a foot on the right. And we want, and whatever is causing that time scale of that and the mechanical response we're considering to be roughly, in the same region. So we wanna do a loosely coupled analysis. And what we do is we essentially say, we want the mechanical response to be quasi-steady as the fluid field changes. So we take a fluid step, the pore field changes, and then we take a bunch of mechanical steps till it's in equilibrium. We take another fluid step, and we do that back and forth. We're never doing them both at the same time because that's super inefficient. The goal here is to let the fluid field change and constantly keep the mechanical system in quasi-equilibrium as the fluid field changes. So we call the fluid process the leader and the mechanical process the follower. Because the fluid process does something and the mechanical adjusts, and the fluid process does something and the mechanical adjusts. That's called a loosely coupled analysis. And we do it by, so we change the boundary condition, we drop it from 14 to 13, so we've dropped it a foot. And then we set the fluid modulus to what we've calculated using those previous expressions as a reasonable one for this purpose, right? We don't use the actual water fluid modulus. We reset our displacement field and our states because again, we want to see the changes, how our state reacted to this. Here we've got both fluid and mechanical on, but this is a key line, we set mechanical follower on. Now it's a follower. What that means is it'll automatically do the substepping process during cycling. Well, if you run this quick, I'm not going to actually run this whole thing. You can see in the cycling bar here, get the mouse out of the way. What's happening is that we've got fluid and mechanical are two separate bars here, and we've got two separate convergence. It's going to keep running to a fluid time. It's here, but it's taking one fluid step, and then it's cycling till it reaches mechanical convergence. And it'll take another fluid step. And you can see this is how many mechanical steps it's taking per fluid step, which we've constrained to be no more than 10 for this. As you can see, we're trying to get to a fluid time of 2.6 e to the 6, but our time step is 0.15. That's going to take a while, even with adjusted fluid modulus. So be aware that these loosely coupled things can be necessary, but they can be very complicated and expensive in the current version, especially if you've got no phreatic surface, everything's fully saturated. If you're in a fully saturated model, then you can increase the fluid time step by using the implicit solver. In the next version of the code, you will be able to use the implicit solver regardless of whether you have a phreatic surface or not, but that's not available yet. Okay. Okay, so now I'm doing better than last time. I want to switch to a different model that will give you sort of an undrained and more two-way coupling example. If I can just quickly show it, I think one is one of the examples that's, I think which, yeah, hope I remember right. Okay. So here we're creating instantaneous pore pressures. Whoop, this is not the right example. Oh, it's right. Okay. If we look at here, what we're doing is it's the title of it is instantaneous pore pressures generated under applied load, and that's exactly what that is. We had an initial system that included some pore pressure and some stresses, and then we added load here. This is the load that was applied, and we're considering this an undrained analysis. So we're not letting the fluid flow. All we're doing is generating pore pressures under that applied load because it's compressing. So we generate pore pressures here immediately underneath that load. We come to equilibrium. And then we say, okay, that happened very quickly. The pore pressure didn't have time to adjust. But then that load stays now. This is like a classic thing. That load stays there. And over time, those pore pressures are going to dissipate. So if we run the next, like this is a, whoop, turn that off. If you run this, you can see that little bulge of pressure starts to drop and spread out. And that's going to cause the mechanical system to adjust as well, as the effective stress changes as that moves all around, all right? That's sort of the short-term versus the long-term effect of a load on a saturated material. And this is one of the examples in the manual. And again, this was done by essentially calculating the load, which in this case we call the instantaneous pore pressure response. We've configured fluid, but we've let the fluid modulus be non-zero here, 9 but we turned fluid active off. So we're just doing mechanical calculations and generating pore pressures, but we're not doing fluid calculations, letting that fluid go anywhere. All right, that generates that instantaneous pore pressure field. And then in the coupled part, we turn both on. Now we're doing the loosely coupled thing. Again, the mechanical is a follower. We're taking the fluid step, mobilizing the pore pressures, it moves, and the mechanical adjusts. And we just keep doing that over time. In this case, the timescales aren't quite so dramatic, so it looks you actually get a solution in a reasonable amount of time. Okay. And I'm done.